Hello, my name is Robert Karban. I will talk in this presentation about my personal experience with Executable SysML using the Cameo Simulation Toolkit from a user's perspective. And during these 5 years of using it, there has been sometimes quite intensive collaboration between Neris, who is the product manager of the SysML simulation toolkit, and myself. So this is the outline of the presentation. I will start with some background about system-level simulation over the years, what's the context and the goals, modeling versus drawing, what's the role of standards in this context. I will talk about the beginnings of the simulation toolkit, some highlights applications, and give some outlook. So the little picture on the right should indicate how I felt sometimes. So pushing the Cameo Simulation Toolkit up the hill as a user because of some hiccups here and there and new features. And in the end, I found out that it's just revolving around the MBSE planet. So it's an evolution, ongoing evolution that will go along with us. So who am I? I studied computer science at the Technical University of Vienna. Then I worked professionally at Siemens Healthcare, Alcatel, at the Particle Physics Lab in Europe, CERN, the National Radio Astronomy Observatory, the European Southern Observatory on major projects like the Very Large Telescope, ALMA, and the Extremely Large Telescope, and mainly in the role as a control software engineer, building control systems for large optical telescopes. Since some time I'm with JPL, working on integrated model-centric engineering, working on the 30-meter telescope, and as a system engineer, and working as a software engineer on the open source model-based engineering environment. I'm a member of INCOSE and a member of the OMG SysML revision task force. I've been using Magic Draws and SysML since about 2007. And on the picture you see that I've spent a lot of time in the field with actual hardware, and here I'm climbing a telescope to push a reset button to get the software started again. So my first experiences with system-level simulation started in 1990, which is already quite a long time ago, where I used a tool called Geode that I used at Alcatel. Geode was a product of a company called Verilog France, which is independent. It's not related to Verilog USA. The tool was based on the STL standard from 88, the Specification Design Language, which is an ITU recommendation. STL has an abstract and concrete grammar and the full form and definition, and uses the abstract syntax notation data types. Geode had a graphical editor and a textual and graphical representation of the language, semantic checker, simple report generators, and some code generation, which did not work very well. And the system was specified as a set of interconnected abstract machines that were extensions of finite state machines. Nowadays, the company went out of business, as far as I know, and there is an open source version of Geode that is around called OpenGeode. The next time I encountered system level in a simulation and used it actively as well was 94, a tool called Foresight that I used at CERN, the Particle Physics Lab, to model accelerated systems. It was produced by a company called Athena Systems, and it was a system design environment that allowed to capture system requirements and designs with in graphical executable models. The models could be analyzed and simulated, and it was a discrete event simulator that allowed in great detail to model network communications and distributed computer systems. And you had an underlying language which was called the mini-spec, which was derived from Ada. That was very strong in abstract data types and was used to describe functionality, whereas topological information was graphically modeled. So it was a combination of graphical and textual modeling. And you had the large libraries for describing network architecture simulations, like queuing mechanisms, and you could literally model thousands of channels at the same time. That was needed, for example, to simulate the experiments of the particle physics experiments. The drawback of the tool was that it was not based on the standard. It was only one provider. All the language features and environment were produced in Nuthina systems, and neither Foresight nor the company are around anymore, I think. So there has been, since quite a while, since more than 20 years already, a need for system level simulation and analysis. It's not really something new. So what is the context and goal for such a model in general? So a model is used to describe a domain or a system, so you can study the system to be built, either the business system, software, and or hardware. And it allows you to gain understanding of the system before or while you're building the system, in capturing high-level behavior in platform independent models. So where you have we are not bound to any particular implementation. You can analyze how the system model reacts to user interaction, or inject predefined testing data and execute scenarios. You can also, if it's executable, explore desirable and undesirable behavior of a future system. And since if the model is the only authoritative source of information, you have consistency across different artifacts that you can transform out of the model, like code, documentation, simulation, analysis results. What one has to pay attention to is semantic consistency, to use the same semantic for simulation, production code, prototyping, but I will talk about that a little bit later. So what's now the fundamental difference between drawing and drawing with Visio and using a modeling tool and a modeling language? So primarily, if you're drawing, you emphasize presentability and drawing skills. You show a number of boxes that not necessarily have a name, some have, some don't, and often some notional connections. But what the actual meaning is and how you can verify this meaning and query the meaning, like in this little example that shows a picture of a transmission, if the front wheels and the rear wheels are the same, you cannot tell from the picture, and since it's just a drawing, you cannot also query something or find out what are the interfaces and how the interfaces work together, or what are the properties of the connections. Now, as soon as you transform that into a real model, like indicated by the little picture on the top right, you suddenly have a database that you can query. And if it's executable model, you can also debug the model. You can validate and verify the design, and you have to model much more rigorously, because for execution the semantics must be unambiguous. It's not just boxes and lines. In the context of UML, having an executable model actually gives you a big leap in understanding UML, when you're actually able to simulate and see what is executable with respect to something with just lines and boxes. If you have it executable, you can also easily generate code from it. You can apply model-based testing and have model coverage, so you can cover a model at model level, the testing, instead of code level, which is much easier. If you have GUI prototyping capabilities, it allows you to demonstrate very early some behavior But sometimes you have to sacrifice some presentability to get computable results. However, with executable models, there are kind of three classes of problems that you encounter. If it doesn't work, for example, if your simulation doesn't work, it could be either a bug in the specification or a feature or in the tool that implements the specification. It could be a user misunderstanding of the spec or of the tool, which is often the case, or the model could simply be wrong. And sometimes it's very hard to distinguish in which category a problem falls if your simulation does not execute, or if your model does not execute. Now, there has been a need, as I said, since long for a simulation, system-level simulation tool and executable models. So what's the role now of the Cameo Simulation Toolkit, and how is it different than the others that I mentioned? So the difference is that it's a framework and provides an infrastructure that allows you to debug and animate, which was also the case with the others. But the big difference is that you can plug engines, languages, and evaluators. You have model-driven configurations and test cases, and it's based on open standards. So actually, the story of Cameo Simulation Toolkit and myself starts in 2008, where NoMagic gathered requirements from customers concerning state chart simulation, model verification, prototyping, modeling languages, and so on. At that time, when I worked at ESO, we suggested to use state chart XML. I will talk about that in a minute. For operational semantics of state chart, because that was not and is still not provided by the OMG, and I still don't regret this choice or this suggestion. And now, 7 years later, Cameo Simulation Toolkit provides you an infrastructure where you can plug engines, different languages, and evaluators, so it has become flexible. It is based on two standards for the execution: the FUML standard for activities and the W3C SysML standard for state machines. You can execute parametric models. You can, with the JSR 223 standard, use different action languages. You have fully featured debugger, animated models. You have some user interface prototyping, and you can have model-driven test cases and scenarios. So the standards play a kind of important role in this picture. The problem with the standards is, or not having standards, is that different tools, if you look at the model, that different tools and libraries interpret the models different. Be it the Cameo Simulation Toolkit, model checkers like Java Pathfinder, or tools like Rhapsody. So different standards also have different semantics. If you compare OMG UML standard versus W3C standard, and UML has started more really like emphasizing graphical notation than having a model behind it. So it has going a long way from some pretty pictures actually to a real model. So if you look at the state machine that is shown here, where you have 4 states, A, B, C, and D, and 2 events on transitions. Well, 1 event on 2 transitions, E1. So if you suppose you're in state B and you would inject an event E1, in StateMate you would go to, it would move to state D, and in Rhapsody, which is a UML implementation, you would go to state C. So depending on the tool, if you look at the same model, it can have very different results when you execute it. So in terms of this executable or semantics that are used for in the Cameo Simulation Toolkit at the moment, one is the FUML from the Object Management Group, which is defines semantics for a foundational subset of UML, and that started in 2005. and it helps you to define structure and behavior semantics of systems. And FUML defines a basic virtual machine for the UML, and so you can execute them. FUML provides only executable semantics for activities, but the very important other part are state charts, and there the SysML standard of W3C is currently supported. This standard provides a generic state machine-based execution environment based on HRL state charts, so hierarchical state machines. And you can describe very complex state machines, including substates, concurrency history, time events, and many more things. The one big difference between the W3C standards and the OMG standards is that for W3C, you need two reference implementation before it actually becomes a standard. And the W3C provides a test suite so you can check the compliance with the standard. So for those who have never seen an executable model, here is a little state machine in combination with some activities that are not shown explicitly. So you have four states in two parallel regions. So it's in state A1 and A3 at the same time, and you have guarded transitions where the guards depend on the state in the other region. So A1 would only go on event S1 to A2 if it's in state A3 on the other side, and the other way around. And the do behaviors and effects on the transitions would send the signals in order to trigger transitions in the other region. So the problem that Nereus faced in the beginning was that FUML does not support state machines, and that SysML engine uses a text document and SysML document for execution. So it's you have to load a file and execute it. So the solution he came up with was to implement a mapping from UML state machine to SysML, which we also have done at ESO, where we have a framework to generate production code from UML models using the SysML engine. Then there was a wrapping of the SysML engine into FUML interfaces, and to wrap the FUML engine into SysML interfaces, so you have a complete integration. So as a result, you have independent engines, and the integration is part of the toolkit. You can use state machines in call behavior actions. The activities or opaque behaviors you can have as an entry do exit behaviors of the state, and send signal actions in activities can trigger transitions in the state machine. And also the UML state machine can be exported to an SysML file, so you can load it in an SysML interpreter and execute outside Magic Draw. So the story of the CST started early 2010, where I got the Alpha 1 version, which was supported on Magic Draw 16.8. It was a file-based interpretation with a file-based FUML engine, so you had to export the model in order to execute it. And there was no support for all the elements in UML, but only for the ones in FUML, which caused some trouble. Some months later, there was CST 1.0 Alpha 2 version, which was refactored with an API-based FUML engine that you could run from within Magic Draw. The biggest difficulty was when you had a model, you did not know it was right until you actually syntactically right until you actually executed it. So we ran into a lot of problems because there was no validation suite that would show you where are the problems. It was a lot of trial and error to actually start to understand what UML and executability is about. And you had a lot of Java exceptions when you did something wrong in this alpha version, which is normal. So there was also a lot of work to set up the simulation, like to start the individual activities of different state machines. So a lot of initial setting it up. Now it has become very easy you have automatic starts. You don't need to specify necessarily an instance tree. You can just run a block or a class with a classifier behavior. It also showed in the beginning that it takes some time to turn FUML into practice to make it usable, because probably nobody has ever used it at that time for some serious work. And in the end of 2010, I gave already the first training on at ISO back at the time, and people were already impressed at that time. But the toolkit was just not robust enough to be used in production. So this is one screenshot from the early days of the simulation toolkit. You had for the ones who knows, there's no separate simulation window. The triggers to inject signals were buttons instead of a drop-down list. There is no debugger, and there are no variables that you can change or modify in the simulation. So very, very basic. So in that alpha, came quite some feedback from my side at that time, which was about model time versus simulation time versus real time, validation speeds for XML, FUML, to have snapshots of simulation state and to define input trajectories to simulations, to have table representation of instance specs, because you have to create instance specs in some cases. The need of an action language, which was not around in these days, and to have execution of multiple diagrams in the same namespace. That the user would be able to select a different context for execution, to check syntax on constraints, to support SysML value types, to execute also without animation for performance reasons, and to be able to debug the model. This is a little bit of an anecdotic slide about the tickets that I submitted over the time. So there were up and downs where sometimes I used it very intensively, then there were periods where I did not use it at all. But in total, over 5 years, I've submitted about 10% of the overall tickets on Magic Draw, and more than half on the Cameo Simulation Toolkit. And the very first actually was November 2010 on version 1.1, which actually got implemented beginning of this year. So all tickets that I submitted have been solved over time. With larger models, and I had some pretty big models that I tried to simulate, it was sometimes very hard to track down where the problem was. So created a lot of small examples to isolate the problem. They can be fixed on the vendor side, and helped also to distinguish between bugs and lack of understanding on my side or on vendor side. But in the end, to provide feedback to vendors is worthwhile if these problems get addressed. And since I had some background on this simulation, I always ask also for new features, and vendors have to make a trade-off of providing new features or work on robustness. So in the beginning, it was more new features and was much less robust. But that has been caught up. So robustness has improved very much in the last years. The last really critical bugs I discovered in beginning 2013, and since that, at least for the purposes I've been using it, has been very stable. So the next step in the simulation story is the cruise control story. So at some point, I wanted to know how the different behavioral models of UML play together. So because I had to build a control system and I needed collaborating state machines, and I wanted to model that. So I looked into integrating state machines, parametric models, activity models. In that case, for just an example, which was a car environment, a cruise control system for a car. And that dates back to November 2011, but it provided a lot of insights on how these things can work together efficiently. So some results were that the action language was extended, that we discovered problems in handling context when you have nested activities in state machines, problems in the FUML, SXML integration. A very important point is to be able to enable simulation of partially specified models, because you cannot always spend a lot of time in order to just to have a simple first cut simulation to fully specified. So in the beginning it was very hard. Now it's easier. You can also partially specified models simulate. And there were also challenges with multiplicities, UML multiplicities in expression and constraint parameters, in particular in parametric modeling. So some highlights that came out of this model was that you could nowadays you can execute parametric models automatically as soon as a value or the parameter changes. Instead of explicitly triggering it, you have support for signal exchange over ports and connectors, which enables you to define encapsulated behavior, and you can record and replay interaction diagrams. So this is a little screenshot of the cruise control domain. So you basically have the car domain, you have a car system and environment, and a simple model of the car domain, which provides models for gravitational force, speed, and brake force. You have the related system model of the car for this simple model. So we're using here specialization to define a variant. You have a vehicle and a cruise controller, and the vehicle model and the cruise controller model for this simple model. And you also have a road model for the environment, which allows you to define the inclination of the road. So here are some screenshots of the involved behaviors. So you have a parametric model, which models the gravitational force, the speed, the brake force model, and uses value properties like the mass of the vehicle, the inclination of the road, or the friction of the road. You have an IBD, which allows you to exchange messages from the cruise controller to the vehicle in terms of speed and torque. You have a state machine, which models the cruise controller itself, where you have engaged state, operating state, suspended state, and you have activity diagrams to implement the PID loop of the cruise control algorithm, and the GUI, which allows you to interact with the model, with the state machines, and shows some state variables like the speed and the torque. So here's a little demonstration where you will start the simulation and start up the vehicle, and then you would start to push your accelerator pedal, and the torque would go up consequently, and the speed would go up, which is shown on the graphs. So the cruise control interaction is on the left, where you can engage, disengage, set the speed, increase, decrease the speed, suspend, or resume. And you could change also the parameters of the PID loop, the KP in particular, the proportional gain. So when you engage the cruise control model and set the speed, here it would not pick up the actual speed, but you have a reference speed, which would be 0. So you would see that the speed would go down, not because it brakes, but because you have a friction of the road. So it bring it down, and the torque would go to 0 because you would not use the accelerator. As soon as you increase the speed, the torque would go up, and as a consequence, the speed and torque would go down and be regulated through the PID controller in order to maintain the speed. Now, the influence of the environment, like the inclination of the road, if you change the inclination of the road, which can be handled through the parametric model, the speed would go down because you go up the hill, and consequently the controller will react and increase the torque in order to maintain the speed. So one other story is also the story of time. So when you simulate systems, you also would like to have something, a model time, which allows you, for example, to execute weeks of operation in like a fraction of the time, like in some minutes or hours. And you want to have a more precise and regulated time than just not rely on the clock of your computer. So since some time, very recently, and then a feature was added to the Cameo Simulation Toolkit, which allows you to specify your own clock. It's a synthetic clock, so you can model the time you want to have. It allows you, I will show later on an example, it allows you to do a debugging based on time, so you can step through your simulation based on time, because you would constrain or define time in your model using duration constraint, and you can do an analysis of all the constrained elements. So here is another highlight that we came up over time, where the Neris had the original idea based on some discussions that I had with him, with other people. It was to have a power roll-up of a hierarchical system based on their states. So you would have here a little system which has a coordinator and 3 components which are driven by the coordinator, and in operating state they would consume some amount of power, and you want to know how this power evolves over time while they are operating. So you have an activity diagram which would communicate from the coordinator to the components to bring them into operating state. The components would have some state machine that where they're in preparing, when they start to prepare to do their job, and when they're in operating. And you would have, and that's the smart part of this model, a recursive parametric model that allows you to roll up the power consumption hierarchically. And you have only one, basically this pattern, and then you apply the pattern, and that's it. So here is a demo. So you have your system product tree with the system that consists of a coordinator and the 3 components, and all the pattern, all the components have the roll-up pattern applied, the parametric model, the activity diagram which distributes the signals over the ports, the state machines of the individual components, and do behaviors in the different states, the parametric model, and the activity while it is operating, where it changes its power. So when you execute this model, it would move to its initial state. You would inject a signal to the coordinator to start preparing it for operation. The coordinator would distribute the signals to the different components over the ports, wait for acknowledgement that the individual components have themselves prepared to operate. They would reply and acknowledge that they have prepared, and move themselves on to operating state. And then the coordinator would also move to operating state. So you see here that the animation goes in both directions, first to the components and then from the components back to the coordinator. And you see here on the bottom right the one variable which is the total power. So that's the total power that is rolled up from the different components. So each component consumes a different amount of power depending on its state. And over the simulation time you would see this total power increasing, and it would be the power of all combined power usage of all the components. Another model we looked into, and also there the Nereus had the original idea how to solve that, it's to change, depending on the state, the constraint in the parametric model. So here it's a model of a system for power analysis, where you have a thermostat, a battery, a heater, and the power state. You have some electrical source, electrical load, and you would change for the thermostat. You would like to change, depending on its state, if it's active or not, to change the constraint that's used for the load. So you would execute this model, and when you change state from idle to active, the constraint actually would change. So you can dynamically change at runtime the constraint that is used, that is initially defined in the parametric model, like here on the load. You would change that on the fly. And that is also a very interesting concept, because it shows you what you actually can do with models at runtime. So application-wise, I've used the Cameo Simulation Toolkit in various instances. Back at ESO, there were 3 major applications: Prima, Ape, and the extremely large telescope. So you notice that the number of components that these models have is about the same, but it differs very much in states and transitions. So for high-level operations of the ELT, where I used to be the control system architect, you have very few states, very few transitions, but on the other ones, on Prima, for example, you have a lot of states and a lot of transitions. And the reason is that the Prima models are used to autocode for generation of code for production system. It's actually in production at the observatory. So you have to add much more detail in order to have an actually operating system, operating control system, which is fully specified in a model. At the JPL, there are 2 main applications I have been involved in to some extent. So one is at the 30-meter telescope, where I work as a system engineer on the active phasing, on the alignment and phasing system, where at the moment the model consists of 16 components, 60 states, 100 transitions and signals, several hundred activity elements, and 60 duration constraints. And the SMAP satellite, where the simulation was used to validate the fault protection system. So that's the biggest state machine I have ever heard about, and it contains 40 components, several thousand states and several thousand transitions, hundreds of regions and signals, and it still works smoothly after. And also there we had some hiccups in the beginning because of the scaling, but they were resolved. So for the TMT, I will talk a bit more about the TMT motivation, why to use simulation. So we want to capture use cases for the alignment and phasing system, and to identify all the involved subsystems in these scenarios, to identify the interfaces and interactions, and to analyze the associated scenarios, like to ensure that timing requirements are met, and also to refine and develop time requirements for the algorithms that are used and the external interface commands. So we do that in capturing the relevant information in the SysML model. That's a database. The information exchange, the estimated required time of the durations of activities. We mimic the message exchange between the different system elements, and we use state machines, activity diagrams, and IBDs for that. So the simulation of the scenarios is based on FML and SXML semantics, and we use a model-based clock, so a synthetic clock, and duration constraints for the precise specification of timing. So to increase the confidence of the correctness, we record the traces of simulation sequence diagrams and inspect them. We ensure that all the leaf elements, by querying the model, have duration constraints applied, so that we don't have any actions in this model that are not constrained. We simulate it, since there it's a limited amount of simulations that we need, that all the actions have been reached, so we have covered the whole space, model space, state space, and we evaluate formally in the simulation also the time against formal constraints, or like a scenario should not take longer than a certain specified amount of time. So here is a demo of the TMT model that I will go through. That's an overview of the current system. So you have the different components. The behavior of the components is specified with state machines and do behaviors. The components are interconnected with ports and connectors, so they can exchange messages. It's basically an asynchronous communication. You will send a command from one component to the other. It would do something and then acknowledge that it has completed the command. The main driver is this piece of model, where you basically have a scenario modeled as a number of states and corresponding do behaviors in the states. So the post-segment exchange alignment use case is modeled as a sequence of states, and the scenario is simply an execution injecting different signals depending on which way you want to take in the scenario, if there is an option. So we look into one of these behaviors, which is the tilt alignment, where you have like an exchange. It would send a signal to another component, which would process the command in its state. So here it's like to take an exposure. On the other side, you would have the state machine, which change the state, and then simulate taking exposure using a duration constraint. In this case, it would be always 37 seconds as the minimum, maximum specified. Now, since this is a model, you can query the model and actually present all the duration constraints in a table. So you would have, sorry about that. The recovery. So you would have the table, and you can view all the constraints that you have the model and review them in table format, which is very convenient. You can also change it there in the table without navigating through all the model and find all the duration constraints that you possibly might have. So you would change it here in the table, and then you see that it changed also in the model from 37 to 38 seconds. You can also use the relation maps in order to explore the full behavioral structure from the top level element through all its components, all the associated classified behaviors, and the states and do behaviors of the states, which is also a very convenient way to see basically to explore the functional behavior, specified behavior. So when you start the simulation, it is based using a model-based clock, as I said. So you would be able to specify here with this little GUI time for how long the simulation should run. So you're able basically to control the time. And also the ratio, like you would say 1 second of simulation time corresponds to like 100 milliseconds of actual run time on my computer. So it's like a kind of a time machine. Say, okay, how does the system look at a specified time? So here I enter 400 seconds, it would stop the simulation, 400 seconds, and the ratio would be 50 milliseconds per second. So would inject the signal to start this particular use case, and start the clock first. inject the signal, it would proceed there to the do behavior. You would see that it would communicate over the ports and using send signal actions with the other state machines, which would execute and acknowledge replies. So you have this handshaking mechanism. You have some at some point you have some user interaction where you have different options in the use case, which requires, in our case, operator interaction to send some commands or don't send some commands. At that time, the clock would be stopped, and you can go for a coffee if you're not sure which way to take the model. So here we are quicker, and so it would proceed. So you see here an overview of all the active states in the various components. I've stopped here the simulation at time 182 seconds. So you could just stop the simulation. Say, okay, in which state are they at which point in time, which is for us very important because we want to know where we can save time in a particular scenario. So then the time moves on. And you see the time counter. You can also do let it run, stop it, and then, for example, single step it through if you want to do so, if you want to have more debugging. So at 400 it would stop. And if we look at the main state machine, which coordinates everything, so here we see all the states again and where they are, which one have been covered, which not. So we can already visually inspect that which ones have been used in this scenario. For example, here the change filter taking exposure in this subsystem was not involved in this execution, and that might be a bug or wanted, a bug in the model. So the active states are the currently active states are the red ones, and the green ones is which were covered. The yellow ones is the last transition. So if you look now at this one, what we wanted to know is how much time is spent between like injecting the trigger and completing the complete sequence all over the system, so including all components. So we take the time at the first transition, and we take the time in between on the intermediate transitions and at the end. And you will see that for the first step in this use case, for the tilt alignment, you see here on the console on the bottom right, the output at the time difference is 221 seconds. So the first basically the first step took 221 seconds, including all the communication and the execution time on all this involved subsystems, on all the other components. So, but the other thing you can, which I mentioned before, is to have to record this execution in a sequence diagram, so you can see in a sequence diagram how these different components interacted at which point in time and how they changed their state. And since it's a model-based clock here, the time will be always exactly the same. And I've heard that in the upcoming version of the simulation toolkit, you can actually use that again to replay and actually validate your model execution against the timings and the state invariance specified in this sequence diagram, which is very nice. And they become rather big if you have a lot of components and a lot of interactions. So for the SMAP satellite, simulation was and modeling and simulation was used to describe and validate fault protection. So fault protection is something, if the satellite flies around, something goes wrong, an error occurs, you have to react to this error and correct the error and try to continue operation. So you would have some error monitors, some responses, you would have some queuing mechanisms. You would have different responses have different priorities. You have to handle one error first before the other. You have different activation rules, and you have system responses if you're not able to handle it locally. So you have like a global reaction across the system, and all this was modeled with a set of collaborating state machines. So you would have all the failure modes modeled, and you can see indicated here on the right hand side you would have the failure modes for the reaction wheel assembly, for example, and you have the different components of the fault protection system, mode manager, error monitors, the fault protection engine, and the local responses, which would react to failure modes and try to remedy them. So the model represents a subset of the fault protection logic of the satellite that was actually launched this year. The SysML state chart was able to capture even the most complicated fault protection logic, because you have a lot of interaction, in particular with different levels of responses and different levels of remedy actions. So the advantages of using that for fault management is that it reduces the risk of gaps in the fault protection. It sets you up for the early verification of the behavior, and since you can link it to other parts of the system model, it enables you to have model-based analysis, verification of the implementation, and you can trace the different elements. So the analysis becomes cheaper with the tools because you can automatically generate reports, you can execute the model, and you can validate the model. So the simulation is used to verify if the behavior is correctly modeled. So the recording of the interactions in sequence diagrams provides some means of verify the behavior after you have run the simulation, and the goal was to run a handful of tests for the different failure modes and to verify that the correct responses occur and the proper actions were taken to mitigate the fault. But since it's a very big state machine, I mentioned before, it's several thousand states, you cannot simulate all the cases. That would take too long. It also would be very boring for the user because you have to interdependencies of multiple simultaneous fault injections, and you cannot thoroughly simulate. So this is where you need another tool, which is a model checking. So we did some model checking on the same model, just transforming it from Magic Draw into using a framework into a language for the Java Pathfinder tool that we used in order to cover the state space automatically. So you would verify simulation that it works initially, the behavior is okay, and then you would use model checking to cover ideally the complete state space. So in the experience I have and for the usages I have, why have I used Simulation Toolkit and what are its current limitations? So it provides you early feedback on the logical correctness of the model. So it helps you to build a correct model, like if you have collaborating state machines to describe a system. You can integrate the different behavioral specifications, parametrics, state machines and activities in order to have a high-level architectural operational simulation analysis. With the pluggable architecture, you can swap in the engines you want, and it supports open standards. And since it's a model that can be exported, you can use your own transformations on the model, so you're not bound to the a vendor-specific implementation. Some drawbacks are that the full XML standard is not supported because it's based on the Apache engine, There's no test suite of the FML implementation provided by OMG, and there's no reference implementation required by the OMG in order to have the spec. So you don't really know, are you having the right FML or not? You don't have no certification of the correctness. If you run big simulations like sequence diagrams, you get a lot of data, and at the moment it's hard to store this data outside the magic draw model, so you kind of pollute the system model with simulation data. And there are potential performance issues for very large models, so recording sequence diagrams like in the SMAP model where you have several thousand states causes sometimes some hiccups in performance, in particular when you animate at the same time. So the outlook is quite interesting, I think, because in particular of the recent integration or support for the of the FMI standard, the functional mockup interface, that it allows you to integrate different rules for co-simulation, different tools for co-simulation. There is some effort going on at the OMG to have better specified semantics. So there's the precise semantics for composite structures, a working group. There's the action language for FUML. OMG is looking into better specify, now it's only English text, the UML operation semantics for state machines, and I really hope that an effort is made to adopt the SysML standard, so we rely on something which has been used over years now and standardized. Storing simulation results outside in a dedicated repository would definitely be a big help. One also should look into support of existing standards like the abstract syntax notation that I mentioned at the beginning of the presentation. Now you have to run the simulation within the Magic Draw tool, but if you have, it would be very nice actually to run it from the server, like without GUI interaction, and also to support like clocked execution, where you have like the clock triggers triggers the actions. The integration with model checking tools would be very, very good. There's still a lot of work for real physical simulations, in particular in terms of performance and reliability of computation, like in our case for technical resource or control margin on a spacecraft. The question that sometimes is asked is, how does it fit? How does this simulation toolkit fit in the current world of all these other available modeling and simulation technology? And we're getting more and more answers to that, like in terms of the functional mockup interface. So like we can integrate that system level simulation with domain specific simulation, but that we still have to see where we go there. And there is a big potential to combine somehow analytical solving of a model, so you don't run scenarios, but you analytically solve your execution, and then can create a model what happened at a particular point in time. And there could be some hybrid approach of simulation and analytical solving. And in case some of you think the simulation is broken, check if the read-only flag on the ports is set to false. So thank you very much for your attention.